online version. It's three-dimensional. You don't even have to wear goggles. And it's edgier watching it live. You never know what's going to happen. Maybe I'll be struck dumb, unable to explain how to integrate over a sphere. I'm not saying it's likely or anything. It could happen. Stay on the edge of your seats. We talked about black body radiation last time. Oh, I forgot to put the thing on. Boy, all those great lines will be lost to posterity. And that's just as well, isn't it? Method to my madness. Here, how's that? Okay, we talked about black body radiation, or black bow deradiation. There we go. So, if we consider radiation in a cavity, like a box, it's in contact with a reservoir. It's at temperature tau. The radiation comes to equilibrium with the reservoir. So what does that mean? It means that if I consider any mode with circular frequency omega, since the energy in that mode will be n h bar omega, if there are n photons occupying the mode, the probability distribution for n in that mode at temperature tau will be proportional to the Boltzmann factor, e to the minus n h bar omega divided by tau. And it would then follow that the expected value in that distribution for the number of photons in the mode with circular frequency omega and at temperature tau would be given by e to the h bar omega over tau minus 1 reciprocal thereof. That's the Planck distribution. Then we can consider summing over the contributions from all the modes to quantities of interest, like the total energy. Well, there are actually two polarizations for each value of the wave number k. So sum over modes means 2 times the sum over all the wave numbers that are consistent with the boundary conditions in the cavity. Yeah.
I have a question. What do you mean by two different polarizations?
What do I mean by two different polarizations? I mean the electric field in a mode. It's physics 12a stuff. Sound familiar? There's an electromagnetic wave. The electric field oscillates back and forth. If it's linearly polarized, and I'm considering an electromagnetic wave traveling in that direction, the electric field can either be oscillating in the this way or that way, right? Can't oscillate in any other way. Those are the two independent modes. They're mutually orthogonal modes. It can, of course, as you anticipate, oscillate in any direction it wants, like this way. But the mode oscillating this way I can think of as a linear combination of this mode and this mode. So for the purpose of counting, there are really two modes. Okay? We're counting the different quantum states, and a general linear polarization can be written as a superposition of two. That's good exercise. And then we considered, in the limit of a large box, replacing the sum over k by an integral. So we had 2 for the number of polarizations. We got a factor of L over pi cubed from the integration measure because of the spacing between the wave numbers in the x, y, and z direction for the modes. And then, because I was integrating only over positive values of k, because I was considering standing modes with fixed boundary conditions, I can integrate over all k, but then divide by 8 in order to avoid overcounting. And if I let k denote the length, of the vector describing the wave number of the mode, integrating over modes means integrating over the length, then times the surface area in k space for a fixed value of the length of the 3 vector. That's the 4 pi k squared. And so I want to integrate, if I want to count all modes, from 0 to infinity, since that's the length of a 3 vector. And so when we do the integral, using this expression for the number of photons in each mode, so the energy is that number times h bar omega in expectation value, we got our formula for the energy per volume of the radiation in the mode, which was pi squared over 15, 1 over h bar c cubed, temperature to the 4th power. Actually, we found it convenient to write this as an integral over circular frequency of a spectral density for the radiation, u omega. U omega was h bar over pi squared c cubed, omega cubed, e to the h bar omega over tau minus 1. So that function u omega as a function of omega, since when omega is small, I can expand the exponential in the denominator, and that goes like h bar omega t. It starts out quadratic, but then eventually it turns over and becomes a decaying exponential for omega large. That's the black body spectrum. In fact, for small omega, which also corresponds to the limit of high temperature, for fixed omega, if I expand for high temperature, I do the same power series expansion of the exponential in the denominator. For omega small, u omega goes like something that doesn't depend on h bar, because this becomes h bar omega over tau in the denominator, canceling the h bar in the numerator. And we just have omega squared over pi squared c cubed tau. Actually, that formula results from the observation that, as we discussed last time, at low frequency, the amount of energy stored in each mode becomes independent of omega. It's just tau. There's energy tau stored in every mode. Well, this is the Rayleigh-Jeans formula. That applies at low frequency. Where it comes from is energy tau in every mode. So it's just tau times this integral corresponding to the sum over modes, except I've written it as an integral over omega instead of k. And if that were the end of the story, as until Planck came along, was the case for all anybody knew, we'd be in trouble, because if we sum over all modes, that means going up to arbitrarily high omega, the integral of the spectral density would diverge. There would be an infinite amount of energy in a finite size box stored in the radiation in the box in thermal equilibrium. Question? This is the energy density, energy per unit volume. Energy tau, that's what it says. Yeah, I guess it's not written very clearly. Energy tau in each mode, right. And so if we, this just becomes tau times a sum over all the modes, and this formula, the omega squared, is just keeping track of how many modes there are with frequency omega. Okay. That's right. Okay. So, let's see. And one other thing we talked about was why we call it the black body spectrum. A black body is one that absorbs any photon that is incident on it. If a black body is in contact with a reservoir, so it comes to equilibrium at temperature tau, it will emit radiation with this characteristic spectral distribution determined by the temperature, the flux, that is, the rate at which energy is radiated by the surface of the body per unit area, is proportional to the fourth power. Actually, it's just given by our expression for energy per unit density times C times a factor of 1/4. So we can write that, defining a quantity sigma b, as sigma b times tau to the fourth. The energy per unit volume goes like tau to the fourth. Sigma b is called the Stefan-Boltzmann constant. And it's just obtained by multiplying what we had over here by C over 4, so that we get pi squared over 60, 1 over h bar cubed, c squared. So that's a universal property for any black body, any one which absorbs perfectly the radiation incident on it. All right, so that's pretty much where we were. Questions about that? Well, now, the next thing we want to do is going to be similar mathematics applied to a different physical situation. Namely, I'd like to consider not photons in a cavity, but the vibrational modes of a solid. Solids are crystalline. There's a regular arrangement of atoms in three-dimensional space in a solid. That's what I mean by a crystal. I'm drawing it in 2 dimensions, but it's really in 3. And let's imagine such a solid is in contact with a reservoir temperature tau. Okay? That's going to cause the atoms to jiggle. Okay? So there will be some energy stored in the vibrations of the solid, and we would like to compute that. What is the energy per unit volume of the solid stored in lattice vibrations at temperature tau? Okay? Well, so what happens? If you look at any one of these atoms, it has interactions with its neighbors. So it sees a local potential. Classically, we can think of the atoms as being in an equilibrium configuration. Okay? Each one is at the minimum of the potential it sees due to its neighbors. And if we gave one of the atoms a little push, it would see a small restoring force, and it would oscillate, right? It would be described essentially by our harmonic oscillator. About its equilibrium position. Well, why harmonic instead of something else? What's special about the harmonic oscillator? Here. Oh, sorry, I thought you were. Okay, we'll take any potential and consider the equilibrium position, which is at the minimum of the potential, so there's no force. The gradient of the potential is 0 there, and then displace slightly away from the minimum. And we can expand the potential in a power series. There's a constant term. Well, nobody cares about that. Potentially there's a linear term, a quadratic term, and so on. But if we're at the minimum of the potential, there's no linear term. And so the power series starts with the quadratic term. And that'll be the dominant term when the oscillations are small, right? So for small vibrations, we can think of the atoms as being a set of coupled harmonic oscillators. It's just like masses coupled together by springs, okay? We take the forces to be linear, the potential to be quadratic. up to higher order terms, which will be small when the vibrations are small. So that's physics 12A stuff, isn't it? Yeah. So it's just a bunch of coupled oscillators. So what do you do when you have a bunch of coupled oscillators in physics 12A? You find the system's eigenmodes or normal modes. So you expand in normal modes. So you can describe the system as a bunch of uncoupled. Since we've now decomposed into normal modes, the normal modes are not coupled to one another anymore. Uncoupled oscillators. And what do we call the oscillations in a crystal? Yeah, I mean, it's sound, right? And when we consider any one of the normal modes, it's just a harmonic oscillator. And when we quantize it, it has equally spaced levels, right? And the spacing between the levels is h bar omega, where omega is the circular frequency of the mode. That's physics 12B stuff. Okay? And so each one of the normal modes, each one of these oscillators, can be in any one of its energy eigenstates. So if it's in its ground state, we say that there are no phonons in that mode. Phonons are the particles that we get from quantizing sound. Just like photons are the particles that arise when we quantize the electromagnetic field, which we also decompose into normal modes and treat each mode as a harmonic oscillator. Harmonic oscillators are great. So in the case of sound, it's not exactly true, but let's take it as a good approximation that the relationship between the frequency and the wave number is one with no dispersion, that the frequency squared is equal to k squared times what? Well, if it were light, what would it be? Yeah, so in this case, it will be the speed of sound. So this is a dispersion relation in which the frequency is linear in k. There's no dispersion. Question? That's a v. So I use c for speed of light, v for speed of sound. Okay. So it's just like light. And because there's no dispersion, the traveling waves will have the group velocity equal to that speed. Those are the sound waves going through the crystal. Similar to light, except we replace the speed of light by the speed of sound.
Sorry, what exactly are the phonons?
The phonons are the vibrating atoms are a system of coupled oscillators. They have normal modes. Each one of those normal modes I can think of as a harmonic oscillator. Quantize that harmonic oscillator, and either it's in its ground state, or its first excited state, its second excited state, and so on. And if it's in its ground state, we say there are no phonons in that mode. If it's in its first excited state, we say there is one phonon, and so on. So we're treating them exactly the way we treated light in the last lecture.
So the difference in phase between consecutive atoms and glass is proportional to the number of phonons in that mode?
The number of phonons in the mode is the amplitude of the mode. So the mode is like some, let's say I have some boundary conditions so that they're free ends. So there's a spectrum of normal modes, and that's physics 12a stuff, I guess. And so for each particular wave number, there's a mode, and the more highly excited that mode is, the bigger the amplitude, that means more phonons. Just like in the case of the electromagnetic field, more photons in a mode means stronger electric field. Okay. It's actually different from light in two respects. Okay? How is it different? How is it different from light? What about the polarizations? How many polarizations are there for a sound wave with a specified wave number? If I'm a sound wave, the atoms are jiggling. That's what a sound wave is. Sound wave is traveling that way. Okay? They could be jiggling horizontally or vertically, perpendicular to the direction of motion, just like with light. Those are two of the polarizations. What else can happen? Yeah, there can be a longitudinal polarization where you compress and release the solid, right? So it gets denser and less dense. So here's what, I'll just draw it in one dimension, what the atoms look like in their equilibrium position, but then I can consider having them bunch up and then get farther apart and bunch up again and farther apart. And so that is a longitudinal sound wave. So there's a wave traveling this way, and the atoms aren't being displaced transverse to the direction of propagation, but along the direction of propagation. Yeah.
Wait, so I was taught that sound waves were only longitudinal.
They can be transverse as well, right? Because when we displace the atoms, transverse to the direction of propagation, there's still a restoring force from the other atoms. Now, it is true that there isn't any general reason why the transversely polarized phonons and the longitudinal phonons have to have the same speed. Okay, they could be different dispersion relations and different speeds. But I'm not going to worry about that type of complication here to keep the math simple, and because it's not too far from the truth. I'll suppose that the three polarizations all have the same speed of sound. So there are two transverse and one longitudinal. I know, you learned about sound in air, right? But this is sound in a crystal. Okay, so there is a restoring force when you displace the atoms in any direction. So we really have three polarizations. And we'll suppose all with the same speed. That the two transverse polarizations have the same speed is true on fairly general grounds because of symmetries. That the longitudinal sound waves also have the same speed. Well, that doesn't necessarily have to hold, but let's say that it does. So that's one way in which sound is different from light. There's another way that's important, that sound is different from light. How else is sound different from light? Well, there is in the crystal a distance scale, the separation between neighboring atoms, right? So is it possible to have a sound wave with a wavelength which is small compared to the spacing between the atoms? No one nodded and several people shook their heads. It wouldn't make any sense, right? What the wave describes is the displacement of the atoms. Okay? So to have a sound wave with a wavelength small compared to the distance between the atoms, there's no such thing, right? So when the wavelength is long compared to the distance between the atoms, they behave a lot like light waves, and they propagate with the speed of sound. But there's a cutoff on how short the wavelength can be, and correspondingly the frequency of the modes. Okay? So the other way in which sound is different from light is there is a wavelength cutoff. So no sound wave with wavelength less than interatomic spacing, or at least not much less. So that means there's going to be some maximum frequency that we have to worry about. There's another way to say that, which is this, that the electromagnetic field in a cavity with fixed volume has an infinite number of modes. That was the problem that Rayleigh and Jeans had. There are modes at higher and higher and higher frequency, shorter and shorter and shorter wavelength, and if they all carried energy tau, it would be a disaster. For the crystal, there are a finite number of modes. So if you have a crystal and it has n atoms, how many normal modes? How many degrees of freedom are there? They can move in any one of three directions, x, y, and z. There are n atoms. Okay? How many degrees of freedom are there in that system? 3n, right? 3 directions of motion for each of n atoms. So the answer is 3n. And what I'm going to do is use the same kind of approximation that we used for a large cavity in the electromagnetic case, replacing the sum over modes by an integral, but I'm going to cut the integral off at some maximum value of the frequency or the wave number, so we don't include more modes than there actually are. So when I sum over modes, it's just like when we were counting the modes for the electromagnetic field, except now we have 3 polarizations instead of 2. So I'll have L over pi cubed and 1/8, and integral dk 4 pi k squared, just like before, except a 3 instead of a 2. Except I'm going to integrate up to some maximum value of k. So I'm going to call it k sub d, which is for Debye. It's the maximum wave number of the sound waves. Well, the corresponding wavelength is essentially the interatomic spacing. So I'm going to figure out what the k Debye is by saying this is the total number of modes, and therefore it's equal to 3n. Okay? So I have what we had for photons, except times a factor of 3/2, because now there are 3 polarizations instead of 2, L cubed over pi squared, and then I integrate dk k squared from 0 to k Debye, which gives me 1/3 k Debye cubed. And that's equal to 3n. Okay, so there's a 3 and a 3 here. I can now write k Debye cubed as a 6 pi squared. And I forgot to say this is, no, that's right. And then here's a factor of volume. So this is k Debye squared equals number divided by volume times 6 pi squared. So up to some numerical factors, the corresponding wavelength, 2 pi over k Debye, goes like the third root of volume over number of particles. That's the amount of the cube root of the volume per particle, essentially the inner particle spacing. Okay? So now we do the same calculation as before, but with the two changes already discussed. We will include 3 polarizations instead of 2 for each value of the wave number, and we'll integrate only up to k Debye. We won't include larger values of k because they correspond to modes that don't exist in the solid. So for the energy per unit volume, I'll have 3 over 2 pi squared, integral dk, k squared, 0 to k Debye, and then the Planck distribution times h bar omega divided by e to the h bar omega divided by tau minus 1. And omega is related to k, just like for photons. Omega is equal to ck, except instead of c, it's v, the speed of sound. So if I introduce the dimensionless variable, so I have a dimensionless integral, which is now h bar v k over tau, then I'm going to be integrating x up to its maximum value x Debye, which will be h bar v over tau times the Debye wave number. So I'm going to call that theta. This is dimensionless, so theta is something with the dimensions of energy or temperature, theta over tau, where theta is equal to the Debye temperature. And from our expression for k Debye cubed, and this definition of theta, we can see what theta is. It's h bar v cubed times k Debye cubed, which is, since we know what k Debye cubed is, h bar v cubed times 6 pi squared and over v. So actually, it'll be convenient for me to write the volume in terms of theta. And n, the number of particles in the crystal, the volume is 6 pi squared h bar v cubed, number of atoms in the crystal, divided by Debye temperature cubed. And when I convert this integral over k to an integral over x, I write omega as vk. So I have dk k cubed, and when I convert it to an integral over x, I'll get 4 powers of tau over h bar v. So I can write the energy per unit volume as 3 over 2 pi squared, and now writing it in terms of an integral over our dimensionless variable, I get 4 powers of tau over h bar v when I replace k by x. And then I also get another power of h bar of v, this h bar times the v that appears when I replace omega by vk. And then I have a dimensionless integral integrated up to x Debye x cubed divided by e to the x minus 1. So this thing is just some dimensionless function now of x Debye. And x Debye is theta over tau. So this is a function of theta over tau. And now I'm going to use this expression for the volume to write the energy stored in the crystal in terms of n, the number of atoms. Because if I do that, there are not a lot of nice cancellations. So if I multiply both sides by the volume, which is 6 pi squared times h bar v cubed, number over theta cubed, all the h bar v's go away, because I'll have 3 powers of h bar v here, and I have 3 powers of 1 over h bar v here. The pi squareds go away, and I get 9 from the 6 times 3 halves. So I can just write this as 9n, where n is the total number of atoms in the crystal, temperature to the 4th, divided by Debye temperature cubed, and then this function f of theta over tau given by that integral. Right? Again, it says so up here, but x Debye, the upper limit of integration is theta over tau. Okay. So that's the answer, but we can appreciate what the answer is telling us better if we consider two limits. Yeah, question.
How do you get cubes over there in the expression of theta?
How did I get this?
Yeah, what do you have?
I got that from the, I guess that was supposed to be theta cubed, right? Sorry. Thank you. So I said theta is equal to h bar v k Debye. Theta cubed, therefore, h bar v cubed, k Debye cubed. And then I used the expression for k Debye cubed that we got here by matching two different ways of counting the total number of modes. Yeah, it's theta cubed. Thank you. Okay. So let's consider the limit of low temperature or high temperature. Low or high compared to what? Yeah, I mean, theta, the Debye temperature. It's a dimensionless function, theta over tau, and we can find how it behaves when theta over tau is small compared to 1 and when it's large compared to 1. So let's consider the low temperature limit first. So low temperature means that x Debye, which is theta over tau, is big. So in general, this x, this function of x Debye is just obtained from the dimensionless form of this black body curve, and then we integrate it up to x Debye. Okay? So when x Debye is big compared to 1, that means we're cutting it off way up here in the exponential tail. So we got to make a very small error by extending the integral, the upper limit from x Debye to infinity, right? Except for some exponentially small error. If it's large compared to 1, we can replace x Debye by infinity, making small error. The error coming from this small tail. And so it's the integral we did last time for black body radiation, the integral of the whole black body spectrum. And that's a famous dimensionless integral. And we used last time that it's pi to the fourth over 15. So that means in this limit we can write the total energy in thermal equilibrium at temperature tau stored in the vibrations of the crystal as 3 pi to the fourth over 5 number of atoms in the crystal times tau to the fourth over theta cubed. Because I just multiplied what I had over here by pi to the fourth over 15. 9 over 15 is 3/5. So this looks a lot like black body radiation. The energy scales like the temperature to the fourth power. So why is it so much like black body radiation? We have a different situation here. There's a cutoff on the wavelength coming from the fact that there's an interatomic spacing, but it doesn't seem to matter. We get the energy going like tau to the fourth, just like the case where we summed over an infinite number of modes. Why did that happen? Well, theta is just h bar omega Debye, right? It's the energy of the frequency at the cutoff, the highest frequency mode, the shortest wavelength mode. And if the temperature is low, that means that these high frequency modes are rarely occupied, right? Because their occupation probability is exponentially suppressed by the Boltzmann factor. So whether they're there or not doesn't even matter. I could have an infinite number of them, but they give a negligible contribution to the total energy because they have exponentially small probability of being occupied, right? So in that case, in the low temperature limit, the fact that there's really a cutoff on the wave number doesn't matter. So cutoff does not matter. High frequency modes have negligible probability of being occupied. And this behavior, in which the energy goes like tau to the fourth over theta cubed per particle, works pretty well when you compare with data for real solids. Well, what do people actually measure? They really measure the specific heat. So if I consider the specific heat at constant volume, that's the integral with respect to the temperature of the internal energy. And so differentiating that gives me a factor 4 from differentiating the tau to the fourth, and then the dimensionless quantity tau or theta cubed. So the heat capacity scales, of course, like the system size, the number of atoms in the crystal, and also like temperature cubed when the temperature is sufficiently small compared to the Debye temperature. So this is called the Debye T cubed law. The behavior of this heat capacity at small temperature goes like temperature cubed. In practice, for real solids, typical values for theta, well, it depends on the solid, but typical values are about 200 to 600 degrees K. But remember, for this approximation to be good, the temperature has to be small compared to theta. So it typically works pretty well at, not at room temperature, but at low enough temperature. So the T cubed law applies for temperatures comparable to 100 degrees K. How cold is liquid nitrogen? What temperature does it boil at atmospheric pressure? 77 degrees, right. So you'd expect to see the T cubed law apply pretty well if you cool a solid to liquid nitrogen temperature and below. (77 degrees K). What about the other limit? That one's easy to do to high temperature. So high temperature means that x Debye is small. The temperature is large compared to the Debye temperature. So that means when we integrate our black body spectrum, we're cutting it off down here somewhere. And that means the quadratic approximation is pretty good. So we can write our dimensionless function as, right, expand the exponential. This becomes x plus higher order stuff. So this is just x squared. So I'm integrating x squared up to x Debye. Approximately, which is 1/3 x Debye cubed. So now what we get for the energy stored in the thermal oscillations is what? We had 9n tau to the 4th over theta cubed, 1/3. And now we have a factor of theta over tau, otherwise known as x Debye, cubed. So we get something quite simple. Because the thetas drop out, and there's 1 power of tau, and I just get 3n tau. That means that the heat capacity in this case, the derivative of the energy with respect to the temperature is just 3n. It's just the number of atoms in the crystal. Okay? Doesn't even depend on the temperature. So what is this telling us? Could we have anticipated that the answer would be 3n tau? Well, 3n is the number of modes, right? So the amount of energy per mode is tau. This is just the Rayleigh-Jeans law again, right? We're in the classical limit where h bar doesn't matter, and each mode carries energy in thermal equilibrium given by tau. Okay? And they're all together 3n modes. So it's just like Rayleigh-Jeans for photons. Except in this case, there's no ultraviolet catastrophe because when we integrate over all modes, we don't sum over an infinite number. We have altogether 3n, the number of atoms. So we get an energy that scales linearly with the number of atoms. Makes perfect sense. In fact, it makes perfect sense to a classical physicist. Well, at least to one particular classical physicist. It's called, by the way, the law of Dulong and Petit. discovered experimentally in 1819, explained by who? Who would explain something like this? Classical statistical physics? Boltzmann. Explained by Boltzmann, who did so many great things in statistical physics, in 1876. That's your default answer when I ask who did something, except let's let the guy have his tea. All right, there we go. He deserves it. Now, who figured out that this wasn't the whole story? That something funny is going to happen at low temperature? So, somebody said in 1906, this is really the tau goes to infinity limit of quantum theory. And something interesting is going to happen at lower temperature. In 1906, he was on a roll. He'd had a really good year the previous year. It was Einstein. And who pointed out that what should happen, if you do things right, is that the heat capacity won't actually be independent of temperature for arbitrarily low temperature. He said that as the temperature gets low, the heat capacity should go to zero. Because he understood that the different frequencies of oscillation of the crystal should freeze out. When the temperature gets small compared to the frequency of the crystal, it won't get excited anymore. Okay, and when you finally get down to zero temperature, the probability of any of the modes being oscillated is very small. The heat capacity goes to zero. He didn't do our calculation, though. He didn't get the T cubed. Actually, in his paper, he could have, but he just considered a toy model in which all the phonons had the same frequency. He didn't consider the frequency spectrum like we did. That was what Debye did in 1912, and that's why we call it the Debye T-cubed law. And it was one of the early successes of quantum theory that boosted confidence that people knew what was going on, that the T-cubed law really was found to hold experimentally, as Debye predicted. Okay. So now I want to talk about a new topic, which is something called the chemical potential. Chemical in quotes, because that's what everybody calls it. And you're thinking, what is this, a chemistry class? No, we call it the chemical potential. It's important in chemistry. It's important for understanding things like the rates of chemical reactions, but it's a more general concept. It's really potential in the sense of potential energy, and we can apply it to lots of different physical situations, but everybody calls it the chemical potential for some reason. I guess because it's important in chemistry. So let's expand a little bit the notion of contact between two systems that we considered earlier. Before we considered two systems, and we said, let's establish thermal contact. And we could imagine that before contact is established, that the two systems have temperatures, tau1, volume v1, and a number of particles n1. I didn't talk specifically about the number of particles before, but now I want to. And then when thermal contact is established, what that means is that now energy can flow from 1 to 2 or from 2 to 1. But the total energy is conserved. So U, the energy of 1 plus the energy of 2 is fixed. But once there's thermal contact, the way the total energy is apportioned between the two systems can change. That's heat flow. And now I'm going to connect the two systems together in another way. I'm going to allow particles to pass from system 1 to system 2. I will establish what I will call a diffusive contact. So you can imagine there's a membrane that's kind of semi-permeable. So you might have a different temperature, at least initially, before equilibrium is established, and a different pressure on the two sides. But particles can penetrate through the membrane. So the number of particles in 1 and 2 are no longer separately fixed, but the total number of particles is conserved. If 1 loses a particle, 2 gains it, and vice versa. Yeah.
Does diffusive contact imply thermal contact?
Not necessarily, although in most cases, because it's true in most applications where diffusive contact does occur, that, that there's energy flow as well. I don't know. The answer is almost yes, because most situations that we consider in which particles can pass from one system to the other, energy can also flow. But conceptually, they're separate concepts. Mathematically, there's no theorem that says if it's diffusive, it has to be thermal. Okay. So now, particles can flow, is what diffusive contact means. But with the total number, N1 plus N2, number of particles in 1 plus number of particles in 2, that does remain fixed. There is conservation of overall particle number. Now, in the case of thermal contact, you'll recall what happens. Once thermal contact is established, the system will seek out its most probable configuration. It will find the way of sharing the energy between the two systems, which gives it the maximum number of accessible states. And what that turns out to mean is that if temperature 1 is greater than temperature 2, then heat or energy flows from 1 to 2 until equilibrium is established. And then the heat flow stops because we're in the most probable configuration. So heat flows from the warmer system to the cooler system until the two systems are at the same temperature. That's equilibrium, where the number of accessible states is maximized. So, similarly, there's a notion of chemical potential. Such that if the chemical potential of 1 is greater than the chemical potential of 2, once diffusive contact is established, the system again will find the most probable configuration with the maximal number of accessible states. And in seeking out the most probable configuration, particles will flow from 1 to 2 until the chemical potentials are equal. And then we're in the most probable configuration, and the system is equilibrated. So I am, as anticipated in an earlier question, going to consider the case where there is both thermal equilibrium, or rather both thermal contact and diffusive contact. Well, suppose I'll call tau the common temperature of 1 and 2. So the two systems are thermally equilibrated. And then I bring the two systems into diffusive contact, so now particles can flow as well. So when we're in the most probable configuration, remember, that means that the free energy, U minus tau sigma, is minimized. And that determines that, so tau now is the temperature, think of that as the temperature of a reservoir. So imagine 1 and 2 are both in contact with the reservoir. That's why they're at the same temperature. Now they're diffusively coupled. Yeah.
So, in diffusive contact, does energy flow as well, or just particles?
Well, we're going to consider the case where there's both thermal and diffusive contact. So both energy and particle number can flow.
Okay, so by diffusive contact alone, it means only particles. Right?
Yes, that's right. Diffusive contact, the term just refers to flow of particles.
Okay.
Right. Actually, so we can imagine that both systems are in contact with a reservoir, so they're maintained at temperature tau. Okay. And now we establish diffusive contact. And now the system is going to try to find the configuration which has the minimal free energy, Helmholtz free energy. It's going to decide to share the total particle number between systems 1 and 2 in the most probable way, the way that minimizes the free energy. It chooses N1, and N2 equals N minus N1 to minimize Helmholtz free energy. So before we establish diffusive contact, system 1 has volume V1, number of particles N1, and system 2 has volume V2, particle number N2. The total Helmholtz free energy is just the sum. And then, suppose some particles flow from system 1 to system 2, or vice versa. So what's the first order change in the free energy? It'll be the derivative of, maybe I should call them, to avoid confusion, F1 and F2. The derivative of F1 with respect to number of particles with temperature and volume fixed, dN1, plus the partial derivative of F2 with respect to N2 with temperature and volume fixed times dN2. That's the first order change in the Helmholtz free energy when the particle numbers change. But because the overall number of particles, the total number, is conserved, dN2 is minus dN1. So let's define the chemical potential of system 1 as the derivative of Helmholtz free energy with respect to number of particles with temperature and volume fixed, and similarly for system 2. So the first order change in the Helmholtz free energy is mu1 minus mu2 times dN1. The system seeks out a more probable configuration by going to lower free energy. So if mu1 is greater than mu2, we'll have dF less than 0, which means we're going to a configuration with more accessible states for dN1 negative. So particles want to flow from 1 to 2, from higher chemical potential to lower chemical potential. Now this is the way we may choose to define. There are other ways of defining it too. Chemical potential, it has the properties that I stated. To seek out the most probable configuration, particles will flow from higher chemical potential to lower chemical potential until diffusive equilibrium is established when the two chemical potentials are the same. All right. So we can use this formula to compute the chemical potential if we know what the free energy is. Let's do that for the ideal gas, because in the case of the classical ideal gas, we worked out everything. Now remember, for the classical ideal gas, or the ideal gas in the classical regime, the low-density regime, we computed the partition function for an n-particle gas as 1 over n factorial quantum concentration times volume to the nth power. Quantum concentration, we recall, is m times temperature, where m is the mass of a molecule of the gas, divided by 2 pi h bar squared to the 3 halves. And the partition function is just e to the minus the free energy divided by tau. So for the ideal gas, the free energy is minus tau, n times the log of quantum concentration times volume minus the log of n factorial. And you can think of the chemical potential this way. I wrote it as a derivative. Of course, the number of particles is actually a discrete quantity. Number of particles is an integer, but when the number of particles is Avogadro's number, there's nothing wrong with thinking of it as a continuously varying quantity. But another way of describing what the chemical potential is it's the way the Helmholtz free energy changes when you add one more particle. Okay? So the chemical potential as a function of temperature, volume, and number of particles is the free energy when the particle number is n minus the free energy when the particle number is n minus 1. How the Helmholtz free energy changes when we add one more particle. So we can see that will be minus tau when the coefficient of the log here changes from n minus 1 to n. We get the log of nq times volume. And then I get the log of n factorial minus the log of n minus 1 factorial from the change in the log of the n factorial term, which of course is just the log of n. And I can combine that together with the other logarithm. It's the log of the product. So it's equal to minus tau times the log of number of particles. Be careful of the minus sign. This minus sign cancels that minus sign. I can write it as n over v quantum concentration, or tau times the log of concentration divided by quantum concentration. Concentration is number of particles per volume. So remember, I didn't yet remind you, the formula really works when n over nq is small. That's when our counting of states is valid. That's what I meant when I said the classical regime. So in that regime, the chemical potential, as we've defined it, is actually negative. But the important thing is how the chemical potential changes when we change the configuration of the system in some way. And what we could ask, what would happen if we have two ideal gases and they're both in equilibrium with the reservoir at temperature tau, but they have different concentrations. Incidentally, because of the ideal gas law, which also applies in this regime, that pressure times volume is equal to number of particles times tau, I can also write concentration n over v as tau over pressure. So equivalently, I can say that the chemical potential of the ideal gas is the log of tau over pressure times quantum concentration. Wait a minute, that's not right, is it? I got it backwards. N over v equals p over tau. That looks better. Sorry. So, right, it should be log of p over tau times quantum concentration. So if we have two ideal gases, two different boxes. They're both in contact with the reservoir at temperature tau, and we connect them with a semi-permeable membrane. So now they can exchange molecules. What's going to happen? Well, what's going to happen? If they have two different concentrations or two different pressures, in order to establish diffusive equilibrium, the higher chemical potential will be the gas with the higher concentration or higher pressure. So to seek out a more probable configuration, the particles will want to go through the membrane from the high pressure or high concentration region to the low concentration region. The particles flow from high pressure to low pressure. Or correspondingly, for the ideal gas, high concentration to low concentration, until the concentrations and the pressures are equal, and that's the equilibrium configuration. Okay. So let's consider kind of a toy problem, a model of the atmosphere. Well, maybe I'm not sure how much of that I'm going to need. So when chemical potential really becomes useful is when we have some external contribution to the chemical potential, which is something that we might be able to control, as well as the internal chemical potential, like in the case of the ideal gas, determined by its concentration. So I might, as an example of having an external chemical potential, have two different ideal gases at two different heights in the Earth's gravitational field. And so the internal energy will be the internal energy of an ideal gas, but it will also include the gravitational potential energy of the molecules in the gas. So since I can write U as what I'll call the external contribution to the energy plus the internal contribution, the external contribution in this case is due to the gravitational potential energy. And the internal contribution is just the kinetic energy of the ideal gas, right? And so the difference in chemical potential between the two gets a contribution from the internal chemical potential difference, which we can get from our formula for the chemical potential of an ideal gas, and the external one. And the external one is just, since this is an energy per particle, the chemical potential is energy per particle, it's just the potential energy cost of lifting the particle by delta H in the Earth's gravitational field, mgh. And so in equilibrium, there will be a difference in the internal chemical potentials of the two gases that matches the difference in their external chemical potentials. the chemical potential well, I said I was going to consider a model of the atmosphere, so let me see if I have time to do that. So here's the ground. Here's the height. Okay? And the chemical potential at some height is going to be a combination of the internal and external chemical potential. In my model, to keep things simple, I'll suppose that the temperature is independent of height. So it's a temperature tau. The chemical potential is the chemical potential of the ideal gas plus mgy. I can think of the gas at different heights as being in diffusive contact. Since the molecules can migrate from one height to another, they can go up or go down by diffusion. So when the atmosphere is in diffusive equilibrium, the chemical potential will be the same at each height. That's the total chemical potential consisting of the internal part and the external part. So this will be a constant in diffusive equilibrium. So we can see how the concentration of the gas will vary with height if the system is isothermal. So constant equals temperature times log concentration divided by quantum concentration plus mgy. So if I divide by tau, and I call this constant mu naught, that means the log of n over nq will be equal to mu naught divided by tau, which is still just a constant, since tau is a constant, minus mgy divided by tau. And so the concentration will vary with the height y. Well, it'll be equal to its value at sea level, at the ground, times e to the minus mgy over tau. Well, you might have anticipated the answer, since it looks like the Boltzmann factor for a system in contact with a reservoir at temperature tau, where the energy is the potential energy, mgy. So in our model, if we put in the numbers, let's suppose that the temperature independent of height is 300 degrees. Well, T equals 300 degrees K. And then mgy over tau can be written as y over a kilometer times 1 over something like 8.0. So the concentration falls off to 1 over E is 1 over E times n of 0 at a height of about 8 kilometers. How high are the Himalayas? What's the height of Mount Everest in meters? Oh, that's feet. Anyway, it's about 8,700 meters, and it's about 8 kilometers, between 8 and 9 kilometers. So according to our model, the concentration should be significantly less at the top of Mount Everest, down by a factor of 1 over E, compared to sea level, which means it'll be harder to breathe. Now, this isn't a very good model for several reasons, although it gives us the right answer in order of magnitude. Well, what's one problem with this model? Yeah, I mean, is it cold at the top of Mount Everest? The isothermal approximation isn't actually all that good. There's another interesting thing about it is that we see that I actually used the concentration of the mass of the oxygen molecule, but the rate at which it falls off depends on the mass of the molecule. So for lighter molecules, the fall off will be slower, and there will be more. Well, which is heavier, nitrogen or oxygen? Yeah. So there will be a little bit. The air will be slightly enriched in nitrogen because nitrogen is a little bit lighter. There's more helium up there too, relative to the rest of the air. The lighter molecules are more likely to diffuse to higher altitudes. Okay. So next time, who knows? I'll surprise you.